Welcome to our discussion session. Let's first start with theoretical exercise 3. Both exercises were mostly about parsing, the practical and the theoretical one. And in the theoretical one, well, these are these typical boring questions like, oh, here's a grammar, do something with it, analyze it, transform it, and so on. Unfortunately, these are typical exam questions for compilers' exams. So maybe you'll see one question like this or so in the exam again. So the first exam was about LL1 parsing, top-down parsing, and we had this pretty strange and useless grammar here. So it's just an example which shows some properties of grammars. So what you have to do to make it suitable for LL1 parsing. And so here we have two problems. So first, from the start symbol, we have two productions with identical prefixes, so ABT and ABTWK. So whenever we read the A, then we cannot decide which of these two productions to take actually, because we would also need to go down to B and T in order to decide if we finally can get a W here. So we need quite a bit of look ahead. And so we've seen in our lecture that there are methods to actually modify such a grammar, which enable us to do LL1 parsing. And so these methods are providing unique prefixes on the one hand and rewrite the left recursion to do right recursion on the other hand, because left recursion, of course, can kill a parser, because when you go down to K, and then try to find a K again, and you go down to K again, well, yeah, that is an endless recursion if you don't take care writing your parser. So what we do is we introduce a new intermediate production here. So now we go from S to the common prefix A, non-terminal B, non-terminal T here. And then after that, we have another non-terminal here, which is a new one we introduce. And this actually encodes the rest of this of these both productions here for S, which is not common. So for the first one here, this is just, well, nothing. So it's epsilon, which always encodes that it's just an empty string. Or it's the rest here, which is WK. So our new production S prime either generates a W and non-terminal K or nothing at all. So this was unique prefixes, and we have a left recursion for K here, as we've already seen, and we have seen we can rewrite this to a right recursion. So when you look at this production, you figure out that there's always at least one S produced, because either you recurse down to KS or you have to generate an S. So this production for K is unable to produce an empty string. So essentially what we need to do is we need to ensure that at least one S shows up here. So we modify our K rule to generate S and then a new non-terminal K prime here. And this new non-terminal K prime then can generate additional S's to the left. Or now we have to change this. It's because we already generated our S up here. We now can finish this recursion by generating just an empty string in epsilon, which would mean K could actually resolve to just a single S and nothing behind it. And that's the same as if we took the production from K to our single S up here. Okay, I think that wasn't too difficult, but that's a typical task you have to do in order to make sure, if you have an LL1 parser, that your grammar actually works with it. So the next question was to tabulate the first and follow sets for the non-terminals and also indicate which of our non-terminals are nullable. So this means they can derive the empty string. Now let's start with the simple ones with nullables here. So nullable is everything that obviously can derive just to an epsilon. So as soon as we have a non-terminal terminal symbol in here and no production without any terminal symbol, then this is not nullable, obviously, because we at least have one character for S, for example. For S prime here, we can derive an epsilon, so this is nullable, so we can have just the empty string. For B, we always have to produce this B here. T, again, is nullable, and K prime is also nullable because we have the epsilon here. So this Last row here is very easy to determine, and the rest is also not so difficult. So to find the first set for S, well, we'll take a look at all the productions for S. We only have one, and the first character for S is always an A, because this is our start production. So for a newly introduced state S prime, we take a look like either it's an epsilon. Some textbooks actually would add the epsilon to the first set. We don't do it. We indicate this nullability. So we just say the first character of S prime is a W, or first token actually. For B, it's also easy. I switched the order around at the table, so sorry. So for B, it's just B. Well, easy enough. For T, it's similar. So either we have an empty string or we have a single T. So we have a T here. And for K, we see it's S for K as well as for K prime. Now the follow set is also not too complicated. So for our starting production, of course, we know that we have to read our whole input text. So the only thing that can follow our S production here is the end of text, so $. And because we split S, the original one, into S and S prime, is also easy to see that after S prime, we're at the end of our input string. So follow for S prime is also $. Now for T, we have to check. So for T, we go down here, A, B, T. So either we have an S prime after this T that resolves to an epsilon. So for T, we have the $. Here. Or we have an S prime that starts with a W. So that is the follow set. So end of text or W. For B, it's a bit more. So our B is here. So either we have a T when we go down to T here, or our T could just resolve to an epsilon. So then it would be the first character of S prime, which would be a W. Or both T and S prime could resolve to epsilons. So B would be our last non-terminal symbol that actually resolves to something. So the follow set of B also includes our end of text. So it's end of text T and W. And for K and K prime, so K stands at the end of S prime, so it's the end of the string, so it's $. And of course the same then for K prime. So here the only slightly more difficult thing is actually to determine the follow set, because you have to be sure to cover all the cases. So you have to find the rules where this non-terminal is actually used, and then go through all the possible combinations of what's coming after this. So if it's non-terminal symbols, you have to recurse through your grammar to find all possible options. Otherwise, well, you might just probably forget one. If you're interested in much more on this, there's something very interesting where you can just input your grammar and just output tables like this. So this would make it much easier to figure this out. There's an online grammar analyzer at this webpage here at the University of Calgary in Canada. And this is very useful to actually confirm that you found the right solutions. Of course, this is also useful in an online exam, so I shouldn't have told you this. Anyways, so we'll adapt obviously the questions accordingly, so it's not quite so simple, but rest assured, it will be manageable. So the final question was constructing the LL1 parsing table of the modified grammar here. So essentially, this is just textbook like it's in the slides. Well, I think you should easily be able to follow this because if I go through all the cases here, essentially, well, that would take a lot of time. And since we have to discuss 2 exercises today, I'll just, well, say, try to reproduce this if you have a different result. Or, well, try to put your grammar into this Grammar Explorer, which I linked on the previous slide. And this also can give you the LL1 parsing table. So it's a really useful tool. So the next question was about LR1 parsing or LR parsing in general. And we have this grammar up here on the slide, which encodes typical simple function prototypes, like you have a type at the start, then you have an ID for a function, then you have brackets around either a list of parameters or a single parameter. And a parameter is a type identifier like int or character or double, and the name of a variable, and params, so this set of type identifier names, are separated by commas. And finally, you have a semicolon here at the end. So the first question was to trace through the sequence of shift reduce actions to really figure out what this LR parser would do on this input here. So we have a typical valid input. It's double, blarf, and then a bracket, then character foo, comma, int bar, closing bracket, semicolon. And we could trace through this. So we could see we have to start from the top here. So for some reason, it always brings up the window title bar here. So it's a bit difficult to see. So we're going from prototype to type, ID, and then stuff in brackets here. So first we have to do a shift to get our very first token in. So this is double. Double is a type, obviously, so we can resolve this using that rule here. So after we read double, we can, after we shifted this in, we can already reduce this to type on our stack, and then we can continue that way. Now, what this should show you is doing this by hand is very tedious and takes a lot of time. And what I wanted to show you in this exercise here is a bit of more intelligent way to actually get output like this. So to really figure out what a parser is doing. And since we already use a parser generator, Yak, we could actually give this grammar to Yak and let Yak do the dirty work here. And this is also very useful when you want to debug grammar. So I maybe should have told you this before the third practical exercise. But still, I think it's very useful. So when we want to do this, we can do this in two different ways. So the first thing we can do is we can actually write a lex file and a yak file. So this lex file always indicates when a rule in this lex file here, so when a match for a token here is taken, then we have a shift of the symbol because we've just read and returned the symbol here. So what we can do in our lexer here, and you see our lexer just has these fixed strings for a data type. It has a typical regular expression for our identifier, which consists of capital and lowercase letters and digits, at least one or more. Then it ignores white space, which is here just space and tabs and new lines. So this is pretty common. And then for all the other characters here, we just return the value of that character. And this string that was scanned by the scanner is always in this global variable YY text. So the first string of that character is in YY text array position 0 here. This is just a character array, so a string. So we actually return this because we also need to find commas and brackets, which are just single characters. You could also just put commas and opening and closing brackets here as tokens and parse them scan them separately. This would also work, but it doesn't bring you any advantage because, well, you can actually, if you just match single characters, you can actually reuse these single characters for matching in your grammar rules, in your Yak grammar. And I think it's easier to read where there's an actual bracket or a comma, which you have to put in double quotes and single quotes, than if you have a token, comma, or something there. So it makes the grammar maybe easier to read, but in the end, it's a matter of taste. So this would already help you printing out your shifts that happen in your grammar, because every time your Yak grammar requests a new symbol from the scanner, it calls this code here, so it is a shift. And then for implementing, the parser, you can actually add a little trick here. So what we can do here is we define a macro we call trace, so it doesn't fill up too much space in each of the rules here. And this trace just resolves to a printf reduce add line. And now we use a bit of compiler magic. So we print an integer, and underline, underline, line, underline, underline is I think it's a GCC and Clang extension. I don't think it's in the C standard. I would need to check it, to be honest. And this actually causes the compiler to replace this by an integer with which gives you the current line number. So whatever, when you start here, It's line number 1, 2, 3, 4, 5. Wherever you use this underline line, it's replaced by the line number of the line where this macro is used. So then for each of the productions here, you can actually add this trace in front of the actual action you want to perform. And this trace then now prints the line numbers. So whenever this action is taken, you know your parser reduces the right-hand side to the left-hand side, because that's exactly when it uses this rule. And so you get an automatic printout that says, okay, we have a reduce, and then we don't have a rule number, but we have a source code line number here. And so if you count source code lines, then you can find out which rule actually was involved. I don't think there's a macro for giving you actually the text of that line, which would be very useful here, so you could print the rule. So this takes a bit of overhead. And when you use this, I've annotated the line numbers here in my source code. So the first production here would be line number 18. The next one, because there's an empty line, would be line number 20, 21, and so on. And when you start and parse your double blarf line here, our example input, then you get the output. First it shifts double, then it reduces at line 21, and we see 21 is a rule that has T double on the right-hand side and reduces this to type. Then we shift the ID, and then this grammar shifts a bracket and a character, and then it starts reducing. It reduces line 20 using line 22, so it reduces character to a type. And then it shifts an ID, which it can reduce, and then it can reduce the character, the type, and the ID using this rule down here at line number 29 to a param non-terminal symbol, and so on and so forth. So you get this output here. So this helps you to debug your grammar to figure out in which state your internal parsing automaton was actually when something fails, or you could just check if all the correct rules are taken. And then I checked this again because I thought it would be nice to have this automatically in Yak. And of course, the designers of Yak also had trouble debugging their grammar, so they added some debug feature. So this is the obvious manual solution you could use, but you could also use a built-in debug function. And you do this by defining a preprocessor constant yyDebug. And then if this yyDebug is actually defined, you also have to set a global variable, which is provided by Yak, called by the Yak library. So you set this yyDebug to 1. And then when you parse it, you actually get a nice output. So all the blue stuff is the output here on the left-hand side, and the black is our input again. So it starts and says it starts to parse. It enters state 0 of its state machine. It has stack 0. So it's in state 0 here, and it reads a token. So now it waits for input. So I enter my line here and press return. And then it starts shifting double. It says next token is token T double. Then it shifts the token T double. Then it says which state it's going to in its internal state machine, gives you a new stack state. And for reductions, it's especially interesting because here for reductions, it says it reduces the stack by rule 3, which here is line 20 now. So the same, of course, we've seen before with our manual annotations here. So it reduces T double to type, for example. And you see, so the original stack contents is T double, this is reduced, and $, our new stack contents is a non-terminal. So token is a terminal, always non-terminal is obviously a non-terminal. And this is replaced by type. Then it enters a new state. This is on the stack. And it reads another token. It shifts an ID, and it reads the next token. And this is much more elaborate than our manual output. So you get 114 lines of output for this example parsing. But it gives you all the details, probably more than you want to know. So you have these two options for debugging your Yak grammar, and I think that's a very convenient way to do this. All right, so the next question was confusing me after all when I tested this out with my Yak grammar. So I seem to have mixed something up here. why does the parser not attempt a reduction to param after pushing the first sequence of type and identifier onto the parse stack? Now, when you look at the Yak debug output for this, you actually see that there's a state which has some, state on the stack already, and then it reads type and ID. So the first set of type and ID we have here, and it actually immediately does this reduction here that I told you would not happen using this rule at line 28 here. So what's going wrong here? I have to figure it out, to be honest, because Yak is not an LR1 parser, but an LALR1 parser, so it's a bit of a different language class. Here I need to dig into the theory, to be honest, to figure out if this actually is just a difference in the implementation or if it's a difference in the approach to parse these language classes, because there is a difference, obviously, between LR1 and LAR1. I need to, we really dig into this, because that was also surprising me. If it also surprised you, that's fine. I'll try to provide an answer to this later on. So this will take a bit of, investigation. The third question was, how many tokens of look-ahead does this parser require? And this question was actually intended to make you think about what look-ahead actually is. So an LRK parser, so a generalized parser with K characters look-ahead, uses the current parser state of its DFA and K look-ahead symbols to decide whether it should reduce. So if that state on the stack is reducible, or if it should not reduce. So the other option is to shift, obviously. And if it decides to reduce, which production to use. So LRK parsers also use a shift transition table to decide which parsing state it should move to after shifting the next input token. And the shift transition table we've seen is keyed by the current state and the single token being shifted, regardless of the value of K. So that means for shifting, for the shift transition table, we always need a look ahead of one token to figure out which state we should move to after shifting. But for deciding whether to reduce or not, that is the K that's important for us here. Then it's a difference in the power of the language, actually, what value this K encodes. So shifting always requires look ahead, even in an LR0 parser, whereas parsing in LR0 doesn't. So parsing, reducing, of course, not parsing, sorry, reducing in LR0 doesn't require look ahead. So what does this mean? This does mean, in other words, that the look ahead is used to predict which reduction should be applied, or if a reduction should be applied at all. So in the LR0 parser, the decision to shift or to attempt to shift must be made before we read the next input token, but the computation of the state, which we are going to transition to, this one is made after reading the token. And at this point, if no shift is possible, then we get an error from our parser. So you can check it. This grammar doesn't need to look ahead to decide to shift. And that's exactly why I wanted to start you in part A with the intuitive analysis. So it is actually a LR0 grammar, which is one of the most simple bottom-up grammars, the most simple bottom-up grammar you can use. So it's actually useful for simple cases like this. But yeah. Okay. But of course, you can do it in a formal way. That would take quite a bit of time to present it here. So if you're interested, you should be able to follow this approach by following the construction of the DFR for the LR parsers from our lecture here. So if you want to prove that a grammar is LR0, you have to build the DFA, so to get the viable prefixes here. And we've seen for constructing this, we always use this additional state from the start state going to a S prime state. So we extend the grammar by this rule to make the analysis easier. And then you need to follow the rules to build the LR0 parsing table. And then you can look at your DFA that you've built, or your parsing table, and the grammar is LR0. if each position in this parsing table LR0 contains at most one element, because then you don't need additional information to decide which of these elements to take, because you have at most one. So it's obvious there is no ambiguity in which has to be resolved by reading an additional symbol from the input. Yeah, so the difference between LL and LR parsers here, to just add some information here regarding look ahead. First, what's common? In both cases, look ahead for LL and LR parsers has the same meaning. So this consists of looking at input tokens without moving the input cursor. So before we do any shift. And for LL and LR, if our K is 0, for an LR parser, we've just seen this, it must decide whether or not to reduce without examining input. If we have an LR0 parser, so we've seen no state in our parsing table can have either two different reduce actions or a reduce and a shift action, because this would mean we have a conflict we can't resolve. For an LL0, so a top-down parser here, this one must decide which production of a given non-terminal is applicable without examining inputs. So this uses the look ahead for a slightly different use case. And thus, if it cannot be allowed to examine any input further, this means for an LL parser, each non-terminal can have only one production. And this means our language is finite. So yeah, this is going into grammar theory. I've gotten some feedback that some of you would probably love to have more practice instead of theory and more backends. This is important stuff, but this, yeah, the whole relevance of compilers has shifted actually from the front end, which was like in the 1950s, 60s, 70s more important, because it was lots of theory you had to actually get right, and you had to get this right with the computing power and memory you had. But nowadays, the importance of working compilers shifts more and more to the back end, so to optimization in terms of performance or energy, to parallelization and so on. So we will never have a compiler course without that theory, but compared to early compiler courses, like we at least have a 50-50 split now, and I think this is going to shift more towards the back end in upcoming years, because this is getting more and more important. Okay, so finally, we had a simple grammar here, and you were asked to construct the parsing table for this grammar, which had just these three rules here. So S would derive two non-terminal x's, and our non-terminal x would either derive a terminal x and a non-terminal x, or a terminal y. And if you tried constructing this parsing table, you found out it's very tedious. And what I wanted to show you here, that already for this very simple grammar, you can get a very complex table for an LR1 parser here. And it looks like this. This is also the one that could be generated by this compiler online tool at Calgary University. And what would be interesting is really to follow the rules in the grammar to figure out where these rules are actually applied in our parse table here. So I won't go too much into theory more today, because we have some practice to cover. So I just need to switch presentations. Probably have to share my screen again. It's a different window. All right, we should be back. Can you see the practical exercise 3 slide set? Yes, thank you. All right, so let's take a look at the practical exercise. And this was, yeah, one of the major parts for building our VSL compiler. So you may have noticed that this might have required quite a bit more work than previous exercises, which essentially means in the first two exercises, you got more points for less work. But building a real compiler is a lot of work, especially if we want to do it in the context of practical exercises here. And since it gets more and more difficult, we decided not to give relatively more points for these exercises, because if you're really struggling with getting that right, this would degrade your grade by quite a bit. So we decided to have this equal weighting of the grades. So if you did very well in the first two exercises, well, that was a bit easier to achieve, I'm afraid. So first task was building a scanner for our WSL language, and sorry for all the typos here, because we tend to vary this language over the years. Sometimes we get stuff mixed up. So essentially in our scanner, this is more or less standard. So one interesting thing is here you can define also stuff like, well, it's not quite a macro, but it behaves like one. So you can define something like white space here and comment and quoted, which you can actually reuse here in the regular expressions. So it gets a bit easier to read. And you can, of course, reuse them several times if you need them somewhere. So what we first do, we ignore any sequence of at least one white space character, which consists of a regular space, a tab character, a vertical tabulator, and a return and a line feed. And then we have this comment regular expression. And this is maybe interesting because this includes the line feed at the end here. So comment starts with 2 slashes like C++ comments or C90 comments. And because slashes are special characters, we have to escape them with a backslash here. And then this last character here is actually interesting because this last character is a negation of this pattern here. So this last character here in these square brackets says anything but the characters included here. So this accent circumflex or hat symbol indicates it's a negation of the pattern. So this means all characters that are not in uline. And then these brackets here group this, and then we have a plus. So it has to start with 2 slashes, and then until we read a new line character, we just, this would match our remaining part of the regular expression here. And this has the result that everything from the start of our 2 slashes to the end of the line matches our comment. And like with white space, we just ignore it. So we eliminate white space and comments first. And then we have just our strings for our keywords here. And sorry, yes, we had 2 examples where we accidentally wrote do in uppercase, because originally this WSL was inspired by old Pascal programming. Pascal programming used uppercase keywords, which is very time consuming to type. So we switched this to lowercase, but we seem to have missed 2 of the do's in the example here. And then we have our typical numbers here, so a sequence of at least 1 decimal digit here. We have our identifier here, and here our identifiers start with either an upper or lowercase letter and an underline, and we have digits, letters, or underlines, at least 0 or more behind this. This is an identifier. And then we have a quoted string, which would just start with a quote, and then anything that's not a quote or a new line until we read the remaining quote here. There's a question on the chat. L shift and R shift. Yes, that's on the next slide. And of course, finally, of course, anything else is returned just as a character itself, y text of 0. So this is the catch-all rule that catches all remaining characters that weren't matched before. So that was exactly the question now. Shouldn't there be some L shift and R shift, and actually also an assign, because we have like assignment as colon equals. We have left shift like the 2 less than characters, and right shift like the 2 right angle bracket characters here. So we can do it that way. So the question is, do we want to detect this sequence in the scanner or write a sequence of 2 characters in our grammar? Both work, actually. I'd say it's a matter of taste. So you can do it that way here, which means you have a pattern colon equals, which returns a sign. We have this left angle bracket pattern, which is also a special character, for our states, which we would employ. So we would need to escape this, and the right angle bracket characters work as they do. And then we have 3 additional tokens. So if you do this, of course, you have to remember to also add these tokens to your grammar to define them there. So then the next question was constructing the tree. So this was more or less building data structures. And we had this node T structure in the IR header file. and you were asked to complete the auxiliary functions that initializes and populates the node and finalize it. And then you could also destroy your subtree, obviously. And node finalize should only remove the memory associated with a single node. So you have these node init functions, and here we can do some tricks to make typing easier. So we can define, well, what I say, like macros that just help you using that stuff here to use the node construction functions. And we call them N0C, N1C, N2C, and 3C. So what we can have in our tree here is nodes with actually 0 child nodes. We can have nodes with 1, 2, or 3. So that's why this node init function is a variadic function, which we call it. So it has a variable number of arguments. And as you can see, we always call the same function node init. We have a fixed number of parameters here in front, and then we can have additional parameters for 1, 2, or 3 child nodes here. And this is something you might not have seen in C before, but which is pretty common. There's a question. What's the purpose of the do while loop here? Yeah, that's essentially a bit of being afraid of C syntax. So do while false, do while is entered always once, and while false ensures that it's actually left after the first iteration. So what this do while loop does is obviously it executes the node init function exactly once, and you usually do this to ensure that whenever you use this macro, it's in a context where you're in a block on its own. So this do while loop is essentially superfluous, obviously. So this is just a little C trick here to ensure that whenever this shows up, it shows in a context that doesn't confuse the compiler. I think for our application, it would have actually sufficed to leave out the do while loop. I can provide you. There's some interesting article on why to do this, but I have to search for it, to be honest. All right, so that's the convenience functions we could use in our grammar here to construct the VSL tree. And then you can have the node init. And so one trick here is, and that's another bit of nasty trick. So we need memory for the node. And this memory for the node could be allocated inside of node init. But then we would need to know how big this node T was. And well, we could do this. But what's done here is that the memory is actually allocated when we call the node init. So this first expression here does a malloc of a memory area that's the size of a node T, returns the pointer to that memory area to n. And when we have an expression like this, n equals malloc, then the return value of the whole expression is the return value of what's here on the left-hand side, so our left-hand side expression. So essentially the value of n is then passed as the first parameter to node init. This is a bit of a strange notation, and it has a problem in my example implementation, as you'll see in a bit, which is a bit nasty. So what we do in our node init function, you see this as a variadic function. So it has 1, 2, 3, 4 mandatory parameters. So the first one is a pointer to a node T, which obviously fits because we are passing it the result of a malloc of the size of a node T. Then we pass a node index T, so a type of the node we want to generate. Then we have a void pointer to something generic, which currently just keeps the information about the type of the node as a string usually. Then you have, we have a uint64 type, which might be a bit outrageous for a compiler. So this indicates the number of children. And then we have additional parameters here, which can include 0. This is valid for additional parameters, or 1, 2, 3, or even more parameters, which we have to get explicitly here. So what we do here is we actually populate that node. So we are getting, we are receiving a pointer to that recently allocated memory. So here we deallocate this. And then we initialize this using this structure in it. So this makes life a bit easier. So you could actually write this like asterisk nd dot type equals type, semicolon, asterisk nd dot data equals data. So you could write all of these each on its own line. And when you write it like this, then, well, it saves you a bit of typing, and it's much more obvious for the programmer that these lines belong together, just filling in a type. So essentially what you do here is you just define elements of a structure here. You typecast this to a node T, and then you'd say, okay, for this node T, the element at type, which has a certain offset in your structure, is initialized to the type we passed. Data is passed to the data. We have an entry of 0. We need this later on. And we have a number of children. And now, depending on the number of children, the amount of memory we need to store our children varies, because we can have 0, 1, 2, or 3 children. So what we do here is we have a children pointer, which is a pointer to a pointer of node T. So a pointer to a list of node T's actually, or an array of node T's. And this allocates, well, number of children times size of whatever we're storing in that node T pointer, because it's just an array of pointers. And this is, yeah, well done to save memory. Of course, if you can waste memory, you could just malloc the maximum number of possible parameters. But this shows a bit of, yeah, because I like to show some C tricks you might see in production code. So this is pretty common. So we don't actually populate the pointers here, but we just allocate memory for the array of pointers. And this indicates if n children is 0, that we actually do a malloc of 0. So it's actually valid to pass 0 to malloc. And then, of course, you get a memory block of size 0. So actually, you get no memory block at all. And now we have to parse these 3 dots here on the right. So essentially, these 3 dots mean variable number of parameters. And variable number of parameters means we can't have any names assigned to them because we don't know how many we have. So what we have to do is we have to pick them out separately. And that's the stupid hack here that's used in C for ages. And this is called VA start. It's a macro actually, stands for start of variable arguments. And so you say, okay, you want to iterate over a child list here. And this child list starts after your argument and children. And then you run a loop from 0 to the number of children that was passed as a last non-variable parameter here. And then you actually set the pointer in our pointer array here that you just malloced here to the argument. So this is retrieved by the VA arg macro. And this goes over this child list here, which we mentioned here in VA start. And then this node T pointer indicates that we want a typecast to node T pointer. And when you finish this, you should use VA end. So this macro does some cleanup afterwards. I actually took a look at how this works when I was like a young student. And yeah, it's really ugly. So I didn't understand it back then. And I think it hasn't gotten any better. I didn't take a recent look at how VR start, VR end works. So this is really an ugly thing in C, but it's of course needed for functions with variable number of parameters. So the typical example would be printf, obviously, which can have an arbitrary number of parameters after its format string. So yeah, this would allocate a node of a given type, of a pass type, and would also then indicate what the children are. If we want to destroy a subtree, we do it we do it well by receiving a pointer to a node T that is at the root of our subtree. And if this pointer is not equal to 0, then we call destroy subtree recursively for the children of that node. And then we do a node finalize to clean up. This is typical tree handling with pointer stuff in C. It's not nice, but yeah, as I mentioned at the very beginning of that course, C is not the ideal language for this. Of course, what you would want is a very convenient tree data type and maybe also graph data types for other things like writing automatons that you can just use without handling pointers and handling destroying subtrees of trees on your own. So that's what makes C a bit nasty to handle for compilers. But of course, once you have these auxiliary functions working correctly, you mostly can forget about them, hopefully. So finalizing the node then gets passed a node. It checks if this is not equal to 0. If its data not equal to 0, then finalize cleans up. So it frees the memory that this existing node's data was pointing to, because we allocated this initially when we constructed the node with node initialize. And then we also do it for all of the children here. And then we free the node to discard itself, set this to 0, and then we have finalized it. So we have cleaned up the memory. If we don't do this, we have a memory leak. So if we have a very large code to parse, this would mean that essentially you would blow up and use more and more memory. That's of course not a good thing to have. So printing the nodes, printing gets past the node T at the level of nesting here in our example. So if this node T of our root is not equal to 0, so if there's something in it, we can print, for example, here the nesting level and the string that we stored here. This node string is indicated by the type here. So a node string is one of the header files. I don't think I have it in the slides. So this is just an array indexed by the type of the node that we were just passed. And then we can check if this type is an identifier or a string or a relation or an expression. We just print the string that we passed when we constructed this node using the initialize function. If it's a number data, well, we can print it as a number here. So we use a long decimal formatting format string here, and then dereference that data. If we stored it as a number here, then we print a new line, and then we would recursively print all the children of our node. And then, well, if we arrived at null, then, well, it's the end, and that's it. We've already seen these convenience macros. I, well, don't need to repeat them here. I don't know why I repeated them. Probably copy and paste error. So for the grammar itself, first you have to do the usual things. So this note, these macros here are part of the first part of your Yacc grammar, so included in these strange percent curly bracket identifiers here. So you include our header file for our VSL compiler. This was already given. So additionally, in the first part, after your literally copied C code, you include your association definitions and your tokens. So we would say for our arithmetic expressions, plus and minus, for example, are left associative, and the same for multiplication and division. And we have a non-associative unary minus symbol here. And then we can have tokens like all the tokens we obviously used in our lex file. And depending on how you decide to do it, we would assign L shift and R shift if you separately scan them in your lex file. And then we have lots of rules. I don't go through all the rules in detail. Most of them are very repetitive. So we know a program starts with a global list. And since we have a global list, we call our constructor with one argument, which is what's on the right-hand side here. So our first thing on the right-hand side is our global list, so $1. And we pass it the information that this is a type program. Our global list has two possible productions. So either it can be a non-terminal global down here, or it can recursively be a global list. And then our global can actually either be a function or a variable declaration here. So functions pass information that is some global stuff here, always passing a pointer to the right-hand side here as $1 as the one parameter. And where's something interesting? Let's go to the next slide here. Let's see. Do we have anything interesting with more than one? Maybe over here. So an assignment statement. So an assignment statement means identifier, assign expression. So here, this is the case where we actually scan this colon equals sign in the scanner and then have assign here. We could also use colon and equals sign separately, each enclosed in single quotes. And this passes two parameters here. So the identifier on the left-hand side, which is 1, child node of the node you're constructing for the assignment. And then we need to pass the expression. And now you always have to take care, because that's the thing I usually fail at when writing YAC grammars and not taking care of what I'm writing, is that I ignore terminal symbols here. So you need to really count. So $1 is the first thing on the right-hand side. $2 is the second thing, no matter if it's terminal or non-terminal. And $3 is the third thing. So I usually think, oh yeah, this is the first thing I think about. So this is $1. This is the second thing I need to consider. This is $2. No, it's not. It's $3. So if you get this wrong, this is a bit difficult to debug, because it's usually such a stupid error, at least for me, that I have a hard time finding stuff like that. So accordingly, we have two parameters. So we call this convenience macro N2C instead of N1C or N0C. All right. I think I'll skip most of this. Of course, if you use L shift and R shift, you have to add expressions for these here also. And well, then finally you have all the other stuff. That's so much. I mean, it's mostly repetitive, just typing from the grammar on the example sheet. And I figured out that it was probably difficult to copy and paste it. So sorry that you had to do so much typing, because sometimes LaTeX produces PDFs that are really, really hard to copy and paste stuff reliably out of. So I should have given this as a text file. I'll take a note for next year. And so this is finally all the rules here. And then we have the rest. So our YY error function, which would just print an error message of the type of the error on the given line using the YY line now global variable here. And this is essentially the rest. So here we don't implement the main function in our parser, but for VSLC, we have a separate C file, which includes our main function, which does the parsing. So this declares a prototype, YY parse, because we have to call YY parse from our YAC grammar, so from our generated C code from the YAC grammar. And then we call YY parse, then we call some simplified tree, which doesn't do a lot at the moment. Then we print the nodes, and then we destroy the sum. Is there a reason to parse number as a number here? At the moment, no. It might be very convenient later for simplifying expressions. So at the moment, it would be perfectly fine to just parse it as a string. So what we do here, a number, okay, yeah. So what we do here, actually, we take the string YY text and we use a function string to long. So we convert the string containing the digits of our number to a long integer, and we store that one here. We don't need to do this, but yeah, later on, it's a bit more convenient to have it as a number already. All right. So when you do this, and I've taken one of the examples here, simplify WSL, you can see one thing where this actually already helps. So we have this two lines with global variables here, A, B, C, D. Then we have a function simplify. I think that should be def simplify here. Sorry, that is copy and paste error from the wrong year of E and F. And then we start a block with begin. Then we assign some value to A minus, and then some expression here. We print this value, and if A equals 0, then we call our simplify function again recursively. And then we return 0 if A is not equal to 0, and that's it. And our output looks like this if we use it like this. And one thing you notice, and that is the simplification you see here, is that this arithmetic expression here would usually give a huge part of your subtree if you stored it as strings. And if you store it as numbers, you can already apply optimizations here. So this is already a strength reduction of the expressions here. So reducing this as far as possible, because our compiler knows its constants. So you can do it in a compiler. We'll look at this, how to do it separately in the intermediate representation in a later lecture. But I just want to show you. And essentially what it gives you here, oh yeah, we have just number data of minus 29 that's printed. That's actually neat, but that's not needed. This is just a little trick I love to show. And that's all.